Okay, so what I want to do here is go over how to do Bodie plots. And we're going to start just by looking at a general example and talking in general about Bodie plots, giving some overall guidelines. Then we'll do a specific example, and then we'll start grouping into rules of how to plot different kinds of terms. So, just as an introduction to Bodie plots, a Bodie plot is used to display the magnitude and phase of the frequency response of a transfer function, h of s. When we've discussed transfer functions, they play a critical role in describing filter performance, but basically a transfer function is an output over an input. Now, as a general rule, there are several steps that are involved in creating a Bodie plot. The first step is that you want to take the s in the transfer function and replace it with j omega. And the reason that we want to do that is, I see I have a spelling error here, I'm going to correct that while I record. The reason that we want to do that is that we're only concerned in this case with the frequency behavior of a system that's represented by a transfer function. So we're not concerned with transient responses that will die away rapidly in time, but we're more concerned overall with how does the system respond to different frequencies. So that's the first thing we'll do. Then we'll find the magnitude of that transfer function, because once we substitute j omega for s, the transfer function becomes a complex number and it has a magnitude or phase. So to do a magnitude plot, we'll take the magnitude of h. To do a phase plot, we'll take the phase of h. Now once we have, for now we're talking about magnitude plot. So once we have the magnitude of h, what we want to now do is we want to take 20 times the log of the magnitude of h. And as you'll see later, the reason we do this is that when you take the log of a function, if a function is a number of products, the log changes that to a sum. And so this puts the units in dB. It changes products in a transfer function into a sum of terms. And the other thing it does is it transforms where things that change over orders of magnitude become more linear, because when we take the log, basically each order of magnitude is represented by 1, 2, 3, and so on. Finally, once we've done that, we're going to plot the contribution of each of these terms as an asymptote, and then we'll fill in the curve in between the asymptotes. Now, as we've seen in the past, Bodie plots are easy to do in MATLAB. So the first thing I want to do before we actually start talking about how to do Bodie plots manually is I want to look at a Bodie plot in MATLAB so that you can get an idea of the kind of information that we get from a Bodie plot. And as we do the Bodie plot in MATLAB, it's going to automatically do a phase plot as well, and we'll discuss that more later. So here is the transfer function that I want to look at. It's 10s over s plus 10 times s plus 1000. So if you've been paying attention in class, you recognize this as a bandpass filter with a lower cutoff frequency of 10 and an upper cutoff frequency of 1000 and a gain that will be determined. So let's pull up MATLAB, and I'll try to keep both screens open at the same time so that you can see both the transfer function and the MATLAB screen. So we'll shrink this transfer function down. So MATLAB automatically recognizes things as a transfer function when you use certain commands. So the first thing I want to do is I want to tell it what the numerator is. So the numerator, and I could call this anything, I don't have to call it numerator. I'm going to use the square brackets, and then I'm going to enter the coefficients of the decreasing powers of s in the numerator. In this case, we have a first order power of s. We do not have a constant. I need to put a zero filler there so that MATLAB understands that that term in the numerator is 10s and not 10. So I have 10 and 0. And then I have two terms in the denominator. So the first term in the denominator is s plus 10. So that can be represented with a 1 coefficient for s and a 10. And then the second term in the denominator is s plus 1000. So I'll represent that with 1 space 1000. And I'll put a semicolon here so that I don't continue to get the echo. Now, if you want to multiply those two terms together in MATLAB, if you just do a straight multiplication, MATLAB thinks that you're trying to do multiplication of matrix arrays, and it will complain to you that you don't have the correct dimensions. So instead, what you have to do when you have terms like this, and since MATLAB is going to understand these to be polynomial terms, you tell MATLAB that your denominator is actually going to be the convolution of denominator 1 and denominator 2. And when you do that, MATLAB is going to give you the coefficients of the polynomial that will result from that polynomial multiplication. So to get it to do polynomial multiplication, instead of trying to do matrix multiplication, you need to use this convolve term for those denominator terms. Okay, and now all we do is we just simply say Bodie of numerator, comma, denominator. And if I don't assign it with a variable name and I don't do anything else, it will automatically return a Bodie plot to me. So here it is right here. Okay, now let's blow this up a little bit and let's see what information we're actually getting. So you can see that the magnitude plot does indeed look like a bandpass filter. We have this region in here where it's relatively flat. It's plotted in dB. And so we show across this flat region that we have a magnitude of minus 40 dB. We'll talk about how to transform from dB to actual magnitude and vice versa. But minus 40 dB actually represents 1 over 100. So, so this would have then a gain of less than 1. And then notice that 10 to the 1, or 10, is represented by this tick mark right here. And you can't really tell, but at this first cutoff, you're down by 3 dB. So this is a minus 3 dB point. Remember that we said the cutoff frequency is equal to 1 over the square root of 2, or 0.707. If you convert 0.707 to dB, you will get minus 3. So you have a cutoff at 10, and then up here we have a cutoff at 1000. So you basically show your bandpass filter here. And then it's not super obvious unless you're really paying attention. But if you go for an order of magnitude here, you actually have a change of 20 dB. So what we say is we are getting a slope on this lower and higher region before and after the cutoff respectively of positive 20 dB per decade on the low pass end, or sorry, on the lower end, which would be the high pass filter, and negative 20 dB per decade on the low pass end, which would be, on the higher end, which would be the low pass filter. On the bottom, we have the phase plot, and so in this particular transfer function, we start with a phase of 90 degrees. We have a phase transition associated with the cutoff frequencies. So there's a phase transition centered around 10, and then there will be another phase transition centered around 1000. So we could almost, without even seeing the transfer function, know that this is a bandpass filter, so there will be an S in the numerator. We know that one of the cutoffs will be at 10. We know that another one will be at 1000. So we could come pretty close to writing this expression based on that Bodie plot alone. Okay, well now let's look at the first step, and I'm going to divide this lecture up into segments because they're hard to watch and hard to track if you're more than just a few minutes. So we're going to divide this into segments. But the one thing I want to do before we conclude this part of the lecture is to show you how, given a transfer function, we put that in what is known as Bodie plot form. So this first line represents our transfer function, and let me go ahead and blow this up into screen view. This first line represents our transfer function, and so you can see that we have the 10s in the numerator, and this is in standard transfer function form. What does that mean? It means that your highest order polynomial, which in this case would be your s per term, or s squared if you were to multiply that out, in the denominator has a coefficient of 1. So it's written in the form s plus a, s plus b, s plus c, and so on. That's standard transfer function form. Now, in order to do bodeplots, because we're making comparisons around significant points, it makes some sense to write this function in a slightly different form. So the first thing we do is for s, we're going to substitute j omega. Why? Because remember, s is equal to sigma plus j omega. It's a complex frequency. And in this particular case, we're only interested right now in the frequency behavior. We're not interested in the transient behavior. So it's the j omega part of s that we want to use as we analyze the frequency behavior. So we substitute j omega in the numerator, and then in the denominator we'll have j omega plus 10 and j omega plus 1,000. Now when doing bodeplots, you want your bodeplot to be something multiplying j omega plus 1. So in the first term, we're going to factor out the 10. So that's what's done right here. The 10 is factored out. So the first term here is j omega over 10, and the second term becomes 1. In the second term, we're going to factor out the 1,000. So here's our 1,000. Here's j omega over 1,000 plus 1. And then a little bit of algebraic simplification puts the transfer function in the following form. Okay, so that's the first step, is to get the transfer function into bodeplot form. In the next video, we will look at the second step and maybe the third step.